So welcome back, and now we're going to follow on from the last lecture which covered the observed climate variations to talk more about how we can understand the future climate. But to do that and even understand the possible causes of those observed climate variations over the last 100 years, we have to model the climate system. And in fact, the climate system is very, very complicated. But to understand the response of the climate system to changes in the energy balance, in the heat balance at the surface of the Earth, we have to use a complex mathematical model of the climate system. This is based around fundamental laws of physics. And so that's what we're going to look at now, is how we simulate the climate system, how these models of the climate system are solved on massive supercomputers, and then how we test the simulations using observational data, how well they simulate variations in the past, and then how we use these models to project what is likely to happen to the climate in the future. So, yes, the climate system is an incredibly complicated system. But what we do is we use mathematical equations to represent the laws of physics and how they govern the behavior of the atmosphere, the behavior of the oceans, behavior of snow and ice, and then the coupling, particularly between all these different systems. The biosphere, vegetation, coupling between the ocean and the atmosphere, coupling between the cryosphere. And there are lots and lots of different processes. And what we have to understand is each one of these is represented by a series of mathematical equations. And these mathematical equations are then solved on computers. But before we can use computers to solve the equations, what we have to do is break up the globe, the surface of the Earth, the atmosphere and the oceans, into a series of boxes or grids, and it's in each of those grids that we're representing the behavior of the temperature, the winds, the humidity, the properties of the atmosphere, or the properties of the ocean. We're also representing things like rainfall and clouds or ice development and exchanges of gases like carbon dioxide between the ocean and the atmosphere. So, the climate models include representations of all of those systems and their interactions and the important processes going on. And so when we look at each one of these boxes, the typical scale of one of these boxes for representing the climate system in the most recent and modern climate models is between 100 and 200 kilometers across, and typically about 1 kilometer in height in the atmosphere. And what we do is we represent the interactions between each of the boxes and the adjacent boxes as exchanges, as movement of air or movement of ocean currents between the different boxes, as well as exchanges in the vertical. These are solved on computers and allow us to predict the future state. And the typical time step that's used in these climate models is of the order of 10 minutes. And they're used then for simulating the climate variations on timescales of 100 years or even longer. And people say, well, wait a sec, if these climate models are the same as the weather prediction models, and we can't predict the weather more than about 10 days in advance, how can we predict the climate? And the reason is because what we're looking at is the average conditions, representative of a longer time period. We're not trying to predict the temperature on a specific day in 100 years. We're trying to represent the typical conditions and how they change. And what we've seen already is that the changes in the energy balance, such as between summer and winter, determine the typical conditions. And the changes in the energy balance are what drives the climate. So we also need reference data to provide the initial conditions for these long-term simulations. We also need lots of observational data to verify the climate model simulations. And so in the last lecture, we heard about the observational data for global temperature around the globe and how it's changed. Well, those data are collected from weather sites, but those data are also used to initialize the climate model simulations. And typically they're initialized in 1850 or in 1900 and then run through the present day period and on into the future. And there's not just one climate model that's run around the world. There's an Australian climate model that's been developed by CSIRO, the Bureau of Meteorology and Universities, but there are also a number of climate models that have been developed in the United States and other climate models developed in the United Kingdom, in Germany, in Japan, in China. There are now more than 30 different climate models that are used around the world to simulate the climate. And what we have to do is to look at, well, okay, we've got to evaluate the performance of these climate models. And the first thing we have to do is, yes, each modelling centre evaluates the climate models, but then there's often inter-comparisons of these climate model simulations. And here's a graph that shows the average pattern of rainfall. In the top panel, it's from observational data, and in the bottom panel, it's the average across a number of these different climate models. And what it shows in these whiter and bluer colours, such as here in the tropics, is the regions of heavy rainfall. And you can see that the pattern is very similar. Heavy rainfall in the tropics, particularly in the Western Pacific region, over Indonesia and Papua New Guinea, than anywhere else in the world. And then much drier regions in the far Eastern Pacific and over areas like Australia. This is the annual average rainfall over a 20-year period from 1980 to 1999. And if you look at these without knowing one's from models or one's from observations, they're actually very, very similar. But an expert can tell because in the observations, the dry areas are just a little bit drier and the wet areas are just a little bit wetter than the average across all the climate models. But generally the pattern of agreement is extremely good. And these are climate models that were started in their simulations more than 100 years ago. We can look at other changes. And for instance, when we look at projections of changes in the thickness of ice over the next 50 years, from roughly present day to the 2050s, the climate models predict or project that the thickness of ice in the Arctic will decline. And we can then look at what's happened over the last 30 years in terms of the thickness of ice. And we see that in 2003 and most recently in 2012, there's been major declines in both the sea ice extent and the sea ice thickness over the last 30 years. And you can see that there's much less ice cover and much thinner ice. So the climate models, when they're running projections from the 1980s to the present and the future, already can be seen to be agreeing well with what we've observed in terms of changes over the last 30 years. There's other ways that we can do evaluations of the climate models, and this is in fact both an evaluation and an experiment, a test. And if we want to understand what have been the major causes of the observed warming of the climate system that I talked about in the last lecture, we need to run experiments. We can't run an experiment with the real Earth system. And the experiment we have in fact been running is one where we've increased the greenhouse gas concentrations. But to know whether that has been causing any climate change or not, we have to run simulations. And as scientists, we have to run repeated simulations. And what we have to do is to run a trial with essentially a case where we have this intervention, increasing greenhouse gases in the atmosphere, and then we run an alternate case, an alternate reality, where we run simulations with no increases in greenhouse gases in the atmosphere, but we run the climate models from 1900 all the way to the present with just natural variability. Changes in sunlight from the sun, estimated from the cosmic rays and sunspot cycles that I talked about in earlier lectures. Changes in emissions from volcanoes associated with dust that end up cooling the climate system. And then we've got all the coupling between the ocean and the atmosphere, and that leads to natural climate variability. So what we're going to do first of all is look at the response in the climate models to simulations from more than 20 different climate models just with natural variability. And that's what's shown in this bottom series of lines down here. The thick line is the average of the climate model simulations run with just natural variations from 1850 right up to 2005. And what we can see is that actually there's major decreases in the simulated temperature every time there's a major volcanic eruption, and this one's Mount Pinatubo in 1991, and actually at the same time there was an observed cooling. Here, if we go all the way back to 1900, right up to 1950, the model simulations and the observations generally agree. If anything, the observations are a little bit warmer here, a little bit cooler here. But remember, this model simulation is an average. The thick line is an average over lots of different climate model simulations. If you look at the thinner lines, they're individual simulations. They show natural variability. But this shows the range that natural variability could cause. And this black line is the observed global average temperatures over the last 100 years. And we see that particularly over the last 50 years, from about 1960 onwards, there's been a pronounced warming in the observed temperatures. There was a warming in the period up to 1950 as well, but that maybe wasn't outside the range of natural variability. But now we see that this recent warming is way outside the range of natural variability. And when we rerun these climate models, but now include the increases in greenhouse gases in the atmosphere and human-caused particles and aerosols due to industrial activity that cool the climate system, we see, first of all, a net warming in the model simulations that agrees remarkably well. In fact, the models that include increasing greenhouse gases with the effects due to human activity, they agree with the observations remarkably well. And this, together with lots of other evidence, has led to the scientists around the world to agree that human activity has very likely been the dominant factor causing the observed warming over the last 50 and 100 years. So these models do pretty well at simulating the last 50 and 100 years. What about using them to predict climate variations into the future? But what we have to do to be able to do that is to understand the future, we have to also be able to predict what's going to happen to greenhouse gas emissions. And to do that, we have to be able to predict what's going to happen to the world's economy, to what's going to happen to the world's energy sources and the world's population. And that's really tough. We don't have a crystal ball that'll tell us what the population is going to be or energy sources. So what the scientists have done, the Intergovernmental Panel on Climate Change, which assesses the climate models and the latest state of science, has used a group of scenarios. And we're going to talk about two different scenarios. We're going to talk about this high greenhouse gas emissions scenario, which is based on business as usual emissions and rapid growth of emissions. And it turns out that the observed emissions over the last 20 years are really following that high emission growth scenario. And we're also going to contrast that to a low emission scenario for which there's a rapid reduction in emissions from burning fossil fuels, and for which there's well, we'll look in a second at what happens to the temperatures, but this rapid reduction in using fossil fuels to generate electricity is then combined with new energy sources from renewable systems, renewable sources like solar power and wind power, as well as major improvements in energy efficiency, as well as technologies like carbon capture and storage, which stops the carbon dioxide from getting into the atmosphere. But I'll talk more about those when I get into the energy lecture. So let's see now what the climate models predict, given those different greenhouse gas emission scenarios, what happens to temperature in the future. And I'm only going to concentrate on two different scenarios: the temperature changes associated with the high warming scenario and the temperature changes related with this scenario for which there's rapid reductions in greenhouse gas emissions. And so for the high warming scenario, when we look at temperature changes on this scale relative to the year 2000, we see the best estimate is warming of around 4 degrees Celsius. The range is up to about 5.5 degrees as well. But it's also important to understand that when we look at these temperatures here in the year 2000, we've already had, in terms of average changes, more than half a degree of warming relative to 1950, and even more when we go back to 1900. 1900, more like 0.6 to 0.7 degrees warming relative to 1900. And what that means is, if we're looking at change relative to the pre-industrial times, the warming in this upper case here is more than 5.5 degrees. Even the best estimate is a warming of 4.5 degrees or more relative to pre-industrial times. Now, the governments around the world have agreed that in order to try to avoid dangerous climate change, we need to seek to minimise greenhouse gas emissions so that global temperatures don't increase above 2 degrees above pre-industrial levels. And that's what's achieved in this low emission scenario. There's actually a good chance that temperatures will remain below 2 degrees. This upper range is around 1.6 or 1.7 degrees above 2000 levels, and it's actually about 2.4 degrees above pre-industrial levels. That means that there is still, even with rapid emission reductions, a substantial chance, a risk of more than 25%, that global temperatures will increase by more than 2 degrees. So even with rapid reductions in emissions, global warming can be even greater than 2 degrees. One of the biggest impacts from warming in the future is associated with sea level rise. We've had about 20 centimetres of sea level rise over the last 100 years, and I talked about that in the last lecture. What about projections into the future? And we see that actually projections of sea level rise are best estimate of about 40 centimetres over the next 100 years, even for this rapid reduction in emissions. In other words, more than half a metre above pre-industrial levels, actually more like 0.6 metres above pre-industrial levels for rapid reductions, and sea level continues to rise. And for high greenhouse gas emissions, there's an acceleration in sea level rise. The sea level best estimate is about 80 centimetres by 2100. Add to that the 20 centimetres we've had already, and the best estimate for sea level rise relative to pre-industrial is nearly 1 metre. And the upper range here in 2100 is well over a metre when we take into account sea level rise that we've had already. So sea level rise is an ongoing problem. And that's because sea level rise is due to expansion of ocean waters. When you heat up the ocean, it expands, and it takes a long time for the heat to penetrate through the deep ocean. And there will be ongoing expansion of ocean waters, leading to ongoing sea level rise for more than 1,000 years, even after surface temperatures have stabilised. That warming of the climate also leads to another dominant factor that affects sea level rise, and that's the melting of ice. Ice on land, when it melts, contributes to sea level rise. Excuse me. And so, melting of ice on land, like glaciers, and particularly the Greenland ice cap and the ice on Antarctica, contributes to sea level rise. And that sea level rise will continue for also many thousands of years. The last time that the climate system was 2 degrees warmer than at present, sea levels stabilised at around 10 to 20 metres higher than at present. It hasn't happened recently, and it took thousands of years, but the last interglacial period, 100,000 years ago, sea level was substantially higher than at present. So 2 degrees of warming is likely to give substantially more sea level rise than just the half metre shown here. That amount of sea level rise, 1 metre of sea level rise, has massive impacts on low-lying areas, such as low-lying countries like Bangladesh here, or even in major well-developed cities like in Melbourne, and in particular in New York. And Hurricane Sandy, when it hit New York quite recently, a few years ago, had a major impact because sea level has already contributed to the average sea level being 20 centimetres higher around New York. That, together with the storm surge, meant that the floods from Hurricane Sandy penetrated and affected much larger areas in Manhattan. If we want to look at the wide range of impacts that there are from climate change, this diagram, which really talks about the climate change impacts in Victoria, a state in southeastern Australia, these impacts are relevant for many, many different areas. There's coastal flooding associated with sea level rise affecting coastal communities all around the world and in Victoria. Many towns and houses in the coastal areas, as well as coastal infrastructure, is subject to flooding from storm surges and sea level rise. And these give numbers for the number of houses affected here in the state of Victoria. There are increases in very hot days, and so the overall warming globally leads to a warming in Australia, and that also leads to a dramatic increase with more than a doubling of very hot days by 2070 from the current numbers. There are major impacts in terms of alpine areas with marked reductions in snow cover, which affects ecosystems, but it also affects water resources. There are changes in rainfall patterns, reductions in rainfall, and those reductions in rainfall have major impacts on agriculture, but they also have impacts on wildfires. And hotter conditions and drier conditions lead to major increases in the frequency of wildfires in areas all around the world, particularly in areas with Mediterranean climates, like in southern Australia, like in California in the United States, like in the Mediterranean regions, as well as North Africa. So in summer, there was likely to be major increases in wildfires due to climate change. All of these impacts are occurring already in many parts of the world. Climate change is not something that is going to impact only in the future. Climate change is already affecting society at present. So let's summarize. Continued greenhouse gas emissions are going to affect the climate system, and our best way of understanding how those projected changes are going to occur and what impact they're going to have is to use climate models, these complex mathematical models of the climate system. But not one model, but many models to represent the uncertainties. And our best understanding is that if we rapidly reduce our greenhouse gas emissions, we have a good chance, but not a complete chance, of global average temperatures remaining below 2 degrees. And that's the level that's been set to try to avoid dangerous global warming. But if we continue on our current path of high greenhouse gas emissions, we're going to have warming of more than 4.8 degrees above 2000 levels, and very likely will have increased impacts in many different systems, including from sea level rise, which is likely to be greater than 1 metre above pre-industrial levels. So these impacts from climate change can be controlled to some extent if we reduce greenhouse gas emissions. And in the next lecture, we're going to learn more about how we can do that and the way that energy use is the dominant factor in driving greenhouse gas growth over the last 50 years and how our energy systems drive the greenhouse gas emissions.